Hello again. We start now the second theme that we will focus. A key factor in understanding the dynamics of coastal spaces, the sea level, we divide into two parts. And these are the basic contents of the topic. In this first part, we will focus our attention on the first four sections indicated in bold black. As has been emphasized before, the coast is the border between seawater and land, and hence the althometric changes of water level are going to be key to understanding evolution of coastal areas in both the short, medium to long term. There are cyclical or ephemeral changes that do not last in time, while others do. The first ones are those of short term. Some authors fix the limit between short and long-term changes in 18.6 years, which is the nodal cycle of the Moon. Short-term changes are associated with astronomical factors, hydrographic and oceanographic, meteorological, and are really important to assess the risk of coastal erosion and flooding, associated mainly to the coastal storms. In this first part, we will focus our attention on all in these kinds of changes, while in the second we will focus in the relationship between climate change and sea level changes. Long-term changes are more definitive in nature and are associated with much slower processes such as eustatics, isostatics, or tectonic. These long-term sea level changes could have less interest for coastal zone management, but climate change has actually brought about a paradigm shift, since probably some of them can be produced soon enough so that it can have a clear impact on our societies, and emphasize the magnitude and frequency of any of the alterations of the marine level to be produced in the short term. So let's talk about the changes in the water level in the short term. They have a different origin, as we have said, meteorological, astronomical, or oceanographic, and the sum of all of them define what we call the total water level. Tides have an astronomical origin, are periodic oscillations, sea level caused by the gravitational pull of the Moon and to a lesser extent by the Sun on terrestrial materials. Seawater, being a fluid, can move because of that gravitational attraction. The effect of the tide changes over time and places. Following well-known patterns, we recorded changes in the short-term sea level in the tide gauges. Look at this chart. How these changes come about in the port of Santander, a macro-tidal coast, and how the sea level oscillates with approximately 2 daily maximums and minimums, and about every fortnight with the most exaggerated tides, what we know as spring tides or neap tides. The range of sea level change on this macro-tidal coast is about 5 meters. If you want to delve a little deeper into the study of this, you can expand this information in this link that you see on screen. Now we show another chart. How the sea level evolves in this same period, but now on a micro-tidal coast like the one in Valencia. We must be struck by the fact that it is not clearly visible here. Neither spring tides nor neap tides. If you look at the range of change from the water level, we will see that is much less, 0.9 meters approximately. The main factor behind these changes is no longer astronomical, as it happened in Santander, but the meteorological one, although the astronomical factor is still perceived in these small oscillations twice a day. The most important meteorological factors are atmospheric pressure, the effect of the wind, and to a lesser extent, changes in water density. One of the most important phenomena for assessing risks of flood and coastal erosion is the formation of that we know as storm surge, that are abnormal rises of water level during coastal storms measured by above the level of the astronomical tide, generated by the action of the strong winds that push the water towards the shore. The abnormal rise in sea level, associated with the storm Gloria that we can see in the graph, is an example of that storm surge. The amplitude of the surge depends the orientation of the coast with respect to the trajectory of the storm. as well as the intensity, size, and speed of the winds, but also of the local bathymetry, if you want to deepen. In this concept, you can see the video of the NOAA that we have contributed here. When the waves advance towards the shore, they suffer a series of small alterations in its geometry that cause a small rising water level known as the wave setup. Its magnitude depends on the characteristics of the waves and the slope of the immediate submerged area to the coast. When the wave finally reaches the shore itself too, advances inland a certain magnitude going up by the coast, in what is known as the wave's run-up. Knowing the sum of the setup and the run-up is very important for know the maximum extent of inland waves. This is essential in order to estimate the risk of coastal flooding. In order to calculate the run-up, it will also be necessary to have information about the slope of the beach, which in turn is very changing. Therefore, this parameter is difficult to obtain. To deepen a little more on the run-up concept of the wave, you can see the video attached that we bring you. All these phenomena, such as the astronomical tide, the over-elevation associated with weather factors such as storm surge, wave run-up, and a good topography of the coastal area, they are essential for estimating coastal flood risks and, to a lesser extent, coastal erosion. But in addition to the changes in water level, i.e., the determination of that total water level, there are other key processes at the time of analyzing possible risks of coastal flooding, as it is the possible subsidence of terrestrial materials and also the position of the water table that can be raised above if sea level rises. And here we close this first part that we have focused on short-term sea level changes.